Okay, let's end this chapter or this module talking about some colligative properties. If for nothing else, to give you a little something else to think about besides calculations, because it's been a pretty calculation-heavy chapter here. Colligative properties are interesting properties that solutions have that change depending on the amount of particles dissolved in a solution. One thing that's interesting about that is that if you have a mole of a sugar like glucose or some other covalent molecule and you dissolve it, you will have 1 mole of particles dissolved in the solution, because each molecule of glucose would be a particle dissolved in the water. Let's say that it's an aqueous solution. If, on the other hand, you dissolved a mole of sodium chloride in water, you would have 2 moles of particles, because we know that the sodium and the chloride go off separately as separate ions, and so we have 2 moles of particles. So these properties would be more affected by sodium chloride than they would be by sugar. They'd actually be twice as affected by sodium chloride. So that's one interesting thing about colligative properties. What sort of properties are they? Well, if you dissolve something in water or in any solvent, you get an increase in the boiling point. The boiling point goes up, and you also get a decrease in the freezing point. The freezing point goes down. So the freezing point of salt water is lower than pure water, and the boiling point of salt water is higher than that of pure water. A lot of times you can do calculations on colligative properties. We're not going to. You might see some resources, if you look into this further, that you calculate what the boiling point or freezing point would be based on the concentration of solute that's in the water. And most of the time, these calculations require the concentration to be reported in molality. That's a concentration unit that we haven't been looking at in this course. I just wanted to mention it here. And as opposed to molarity, which is moles of solute per liter of solution, molality is moles of solute per kilogram of solvent. And one of the reasons why this is a very useful concentration for calculating these colligative properties is that if you put twice as much solute into a solution, the molality will actually double, because adding more solute affects the numerator only, not the denominator. The kilograms of solvent are not going to change. If you have a kilogram of water and you put 1 mole of solute in it, and then you put an additional 2nd mole of solute in it, you've just doubled the molality. You don't quite double the molarity when you do that, because if you put a 2nd mole of solute, you're going to slightly change the volume of the solution. Dissolving more stuff in water is going to not double the volume, obviously, but it will slightly increase the volume of solution. So you'll double the numerator, but you'll also slightly increase the denominator. So the molarity will not double. And then, of course, with the mass percent, if you put a 2nd amount, double the amount of solute that's in there, you're increasing the amount of solution as well. So that mass has to also be added to the denominator, because you're talking about solution. So if you double the amount of solute that's in a solution, you are not going to double the mass percent, you're not going to double the molarity, but you will double the molality. And you also will double the effect of the colligative properties. So that's why having the concentration in molality is better for doing calculations of this type. But we are not going to calculate the molality of things. We're just going to take a look qualitatively to what's happening in these solutions. So we just want to know that the more solute we have in a solution, the further up the boiling point is going to be elevated, and the further down the freezing point is going to be depressed. All right, so here I've written out a little summary of what we've learned here. The more solute a solvent has in it, the higher the boiling point of that solution, and the lower the freezing point of that solution. So since we want to know which one has the higher boiling point, we want the one with more solute. So the answer to this one would be the one with the higher concentration, which is the 0.734 molal sodium chloride solution. For this one, we want to know which one has a higher freezing point. The one with more solute has a lower freezing point. So this time the one with less solute will have a higher freezing point. So we will want the solution that has less concentration of sodium chloride in it. So between these two solutions, the one with less sodium chloride in it will have the higher freezing point. The one with more sodium chloride in it will have the higher boiling point. So this one's just sort of a bonus question. I said that we weren't going to calculate molality. If you want to try it, this one is in the answer key. I'm not going to be asking this on the assignments in class, but if you're curious and you want to try one of these calculations, you can do that. I know that we have a lot of biology majors, biochemistry people in the class, and so one of the colligative properties that you might find interesting is osmotic pressure. Osmotic pressure is caused by the tendency for a solvent like water that can flow through a membrane to try to flow through a membrane in such a way to even out concentrations. So if we have two solutions separated by a semi-permeable membrane, so here's our semi-permeable membrane here, and the water can flow through this membrane, but the things that are dissolved in solutions A and B cannot get through the membrane. So whatever kind of solute is dissolved, those molecules are too big, or the ions are too big, or this membrane won't let through anything that's charged. For some reason, those solute particles cannot get through. Only the water can get through. So if we have these two solutions with different concentrations, A being more concentrated and B being less concentrated, the way to even these out would be for water to flow in this direction, from the less concentrated to the more concentrated. That way A will get more dilute, B will get more concentrated, and their concentrations will be more even. And so the water is going to flow from an area of lower concentration into an area of higher concentration, so that the concentrations become closer to each other. And the way that that would end up looking, if water flows in this direction, the volume of B is going to go down, concentration is going to go up, but the volume is going to go down, and the volume of A is going to go up while the concentration decreases. So their concentrations are now closer, their volumes are further apart. If we had the opposite situation with A being less concentrated and B being more concentrated, this time the water is going to flow in the opposite direction from A to B, and we will end up with a lower volume in A and a higher volume in B. So this property is pretty useful. It's used in water filtration systems. It's used in kidney dialysis. And it's also important when you are considering the concentrations of fluids that you inject into the bloodstream, like maybe an IV. If you're giving someone some fluids by IV, you shouldn't give them pure water, because then you're introducing a solution into the bloodstream with a different concentration of solutes than the bloodstream is used to having. And that can affect the behavior of the red blood cells that are in your bloodstream, because the cell membrane for different cells is a semi-permeable membrane. It lets some things through, but not everything. So it's very similar to that membrane we saw above in the diagram with the A and B solutions. So a red blood cell is not made up of 0.9% sodium chloride, but it has the same concentration of solutes as a 0.9% sodium chloride solution would have, and so this is a useful number to use as a benchmark for red blood cells. So here's our red blood cell, and it has the same amount of particles as a solution of 0.9% sodium chloride would have. So if you put that cell into some sort of beaker, other container, test tube perhaps, that had a 5% sodium chloride solution, we are going to have water flow from an area of low concentration to an area of greater concentration to try to even these concentrations out. So we are going to have water flowing out of the cell in this case. that will cause it to shrivel up as the water flows out of it. All right, so what if you put some red blood cells in a solution with no salt in it, just plain water? So now we have 0% sodium chloride on the outside and 0.9% on the inside. So water will flow from the area of lower concentration to the area of greater concentration, and we will have the cell swell up and burst with water flowing into it. So this is why an IV drip should not be just plain water. If we were going to have an IV solution, or if we were going to have a solution in our test tube that we wanted to store some red blood cells in without killing them, we should get something that is 0.9% sodium chloride or equivalent to that as far as the concentration of particles. So if you read more about this phenomenon, you might come across these vocabulary terms. Isotonic would be something having the same concentration of solute. So two solutions would be isotonic if they both had the same concentration of solute. So this last example, the 0.9% sodium chloride solution, would be isotonic to the cell because they have the same concentration. They would both be isotonic to each other. If you have two solutions with different concentrations, one would be hypertonic and one would be hypotonic, just depending on which one you're referring to. So here, in this case, the solution is hypotonic and the cell itself would be hypertonic because it's higher. And in this case, the solution is hypertonic and the cell is hypotonic. So I was teaching this once to some students who were also learning a similar concept in their biology class, but the biology class was referring to the cells as hypotonic or hypertonic, and my textbook was more focused on the solutions as hypertonic and hypotonic, and the students were getting confused thinking that one of us had it backwards, but it just depends on whether you're referring to the solution or the cell. The cell bursts when the solution is hypotonic, but they were learning that the cell bursts when the cell is hypertonic, and both of those are true. The cell will burst when the solution is lower in concentration and the cell is higher in concentration because the water will flow in and make the cell swell up. So is that a hypotonic situation or a hypertonic situation? It depends on whether you're looking at the solution or the cell.